Hello, I'm Molly Mackay-Smith, Product Development Specialist at Maui Media Lab, LLC. I want to talk to you today about revolutionizing the electric utility market through the use of digital power. Digital power uses commodity cloud supercomputing based on application-specific integrated circuits, also known as ASICs, creating cryptocurrencies to maximize potential revenue per kilowatt hour earned from generating, storing, and transmitting power. Digital power offers benefits for utility-scale generation, storage, and transmission of electricity based on traditional fossil fuels, as well as renewable resources including geothermal, the sun, and the wind. Digital power is made by using electricity to power specialized ultra-high-performance application-specific integrated circuits, ASICs, to provide value-added networked commodity cloud supercomputing services in exchange for cryptographically authenticated proofs of work, known as cryptocurrencies. Cryptocurrencies are readily convertible to national currency at market rates by licensed exchanges. Currency can be redeemed at a later time or at a different place for generator fuel, infrastructure investments, solar panels, carbon credits, trees, and more. Surplus currency represents an additional source of shareholder value. Just like analog electricity, digital power can be both stored and transmitted. The benefit of digital power, however, is it can be stored almost indefinitely, regardless of storage time, and transmitted over any distance, regardless of location. This unique characteristic of digital power offers some truly revolutionary opportunities to address both curtailment loss and transmission cost issues for feed-in tariff power providers, solve grid integration issues for net electric metering clients, and help eliminate reliability issues for local grid customers. Digital power simultaneously can offer significant reductions in cost and engineering complexity issues, typically associated with high-voltage long-line and offshore electricity transmission. An electric utility's time, money, and resources are ultimately expended in order to create and provide one consistently smooth analog electrical waveform, capable of simultaneously serving all of its customers' requirements. Traditionally, this was a fairly straightforward process of ensuring an affordable fuel supply for the utility's generators, and ensuring that the generators are properly functioning and that electricity is flowing over power lines one way, from the utility to the customer. Contemporary governance mandates arbitrary feed-in tariff, FIT, and net energy metering, NEM, that require the utility to accept and integrate power from third-party power providers, in addition to their traditional role of generating and transmitting electricity for its customers. Current industry efforts demonstrate that upgrading the traditional one-way analog power grid to bidirectional smart grid is expensive, unreliable, and ultimately impractical and unsustainable from both the engineering and business case perspective. Analog integration requires a two-way grid equipped with dynamic voltage regulators, smart meters, and inverters to synchronize the many disparate FIT and NEM power sources with the regulated utility grid. This requirement becomes exponentially more complex with the addition of every FIT third-party power provider and every single NEM customer. In the best case, servicing NEM customers with an analog smart grid, as is currently the practice, provides no economic benefit to the utility, since power is both sold to and purchased from NEM customers at the same rate. Ultimately, any attempts to provide NEM service with an analog smart grid are inflexibly constrained by the fact that local circuits effectively require that at least half of a utility's customer baseload users do not qualify for NEM rates. FIT power providers are typically interconnected to the grid via expensive dynamic voltage regulators, battery banks, and analog high-voltage copper transmission lines. The cost of the transmission line, as well as power transmission efficiency, are a function of and ultimately limited by the distance between the FIT power provider and the utility interconnect facility. Additionally, renewable FIT-regulated third-party power providers are subject to significant and unpredictable curtailment losses. According to Henkels & McCoy 2013 report on renewable utilization in Maui County, in only 1 year, Maui Electric and their renewable-based feed-in tariff, FIT, power providers lost 66 gigawatt hours of curtailed electricity, equivalent to $33 million of lost income from power generated when it was not needed and could not be sold. Storing analog power requires expensive and potentially hazardous chemical batteries or a system of pumps and hydroelectric dams. Chemical batteries and hydroelectric dams incur up to 40% economic loss when operating properly. And when chemical batteries and hydroelectric dams fail, they fail spectacularly, often with tragic results to people, damage to property, and ultimately blight our environment. A digital smart grid eliminates all of these issues, typically identified as analog smart grid problems, by converting the renewable energy generated by FIT power providers and NEM customers to digital power on-site, and channeling this digital power back to the utility over existing optical fiber, wireless, and satellite internet infrastructure. Channeling digital power back to the utility in this manner allows the existing and installed analog electric utility infrastructure to be used in the manner it is intended, as an efficient means of transmitting consistent, reliable electricity one way, from the utility to its customers over existing wires. With digital power, grid disruptions from improperly interconnected or improperly operating FIT and NEM installations, or from the ebb and flow of renewables as the winds die and clouds dim the sun, will no longer be a problem. While there is a 1% cost incurred converting digital power back to analog power, the analog to digital conversion process provides additional value in the form of a market rate economic benefit, equal to the difference between the cost of 1 kilowatt hour of electricity and the cost of 1 ASIC kilowatt hour of commodity cloud supercomputing, which is recorded at between 7 and 20 times fuel cost rates between November 2013 to the present, March 2014. What is the cost commitment of building out a digital power-based smart grid? At current market rates, March 2014, electricity can presently be converted to digital power at a one-time installment cost of roughly $10 million per megawatt of digital power conversion capability. And because we are transmitting and storing digital power, distance and density are virtually unlimited. Capacity scales linearly with cost. At current market rates for fuel, 20 cents per kilowatt hour, and regulated rates for FIT power providers, 21 cents per kilowatt hour, along with the current market rates for commodity cloud supercomputing, $1.50 to $4 per ASIC kilowatt hour, complete recovery of installation costs are projected within 12 months. Let's dream big. Digital power may just be the answer to Hawaii's electric problems. The most efficient way to interconnect electricity generated by third-party FIT-regulated power providers and NEM-regulated utility customers is to convert it to digital power on-site and channel it back to the utility via the existing fiber optic, wireless, or satellite broadband internet infrastructure. Since digital power transmitted back to the utility can be either used immediately or stored indefinitely, curtailment losses resulting from an excess of renewable FIT and NEM regulated third-party power, when it is not needed and cannot be sold, are completely eliminated. Additional value from the digital power conversion process, in excess of mandated prices regulated by FIT and NEM rules, is returned to the utility as a new recurring income channel. Additionally, with digital power and a digital smart grid, caps on the number of NEM customers allowed on a local circuit can be completely eliminated, allowing more customers to qualify for NEM electricity rates and allowing more rooftop solar photovoltaic systems to be installed throughout the entire service area. The potential for saturating a local circuit with too much renewable generation capacity is no longer even an option. A considerable amount of discussion and proposed legislation continues to be had with regard to the subject of connecting the Hawaiian Islands of Lanai, Molokai, and Oahu with high-voltage submarine long-line electricity cables. The cost of only a single segment of this proposed high-voltage submarine long-line electricity cable has been estimated at $1.5 billion, ensuring that such a cable would be cost-prohibitive, and construction of such a cable would likely require significant rate increases to customers and/or additional public bond issuances or other government subsidies. The most efficient way to transmit power long distances, by land or by sea, is to convert electricity to digital power on-site and channel it back to the utility via the existing fiber optic, wireless, or satellite broadband internet infrastructure. Transmitted digital power incurs only a 1% loss when converted back to electricity, regardless of the distance the digital power is transmitted. Additional value resulting from the process of converting analog electricity to digital power in excess of mandated prices regulated by FIT rules is returned to the utility as another new recurring income channel. Since digital power can be transmitted via existing internet infrastructure, archipelagos like the Hawaiian Islands can realize the goal of connecting their local island circuit into a single digital power-based smart grid, using their already existing and already installed fiber optic and even wireless and satellite-based internet infrastructure, and without sinking huge sums of public money into dubious projects on the pretense of connecting the islands separated by open ocean with expensive copper cables. Digital power transmission also offers the possibility of economically viable over-the-horizon offshore wind farms, with on-site digital power conversion interconnected back to the utility via a combination of relatively inexpensive submarine fiber optic cable and wireless network segments from virtually anywhere in the internet-connected world to virtually anywhere else. Stored digital power incurs only a 1% loss when converted back to electricity. Additional value resulting from the process of analog electricity to digital power conversion in excess of mandated prices regulated by FIT rules is returned to the utility as another new recurring income channel. Digital power and a digital smart grid improve local circuit reliability in two distinct ways: by using the digital network to channel digital power from third-party FIT power providers and NEM customers back to the utility instead of connecting the generating capacity of these third-party power providers directly back to the analog grid, and by offsetting the spinning reserve fuel costs. Electric utilities are required to operate an always-running emergency or spinning reserve, which can provide additional electricity generating capacity from the traditional oil-fueled generators, capable of keeping the electric grid stable in case of a primary generator going offline. An electric utility is also required to keep reserve generators capable of covering the potential output of all non-firm connected renewables, such as wind turbines and photovoltaic panels. Traditionally, this spinning reserve is viewed strictly as a cost-only liability, in that fuel is spent on idle generators for which no electricity is being sold. As long as the market price for an ASIC kilowatt hour exceeds the regulated price of fuel per kilowatt hour or feed-in tariff, it is possible to create value from spinning reserve by redirecting the spinning reserve load from analog electricity to digital power conversion. Since the ASICs used at the heart of the digital power conversion process can be turned off with fast automated demand response in milliseconds, unlike generators which can require several minutes, spinning reserve power is available to the grid when it is needed, with no delay. However, when surplus spinning reserve becomes available once again, ASICs can be instantly turned back on and electricity can be redirected to the digital power conversion process. Additional value resulting from the process of analog electricity to digital power conversion, in excess of spinning reserve fuel costs and/or mandated prices regulated by FIT rules, is returned to the utility as another new income channel. Digital power conversion uses electricity and produces only heat as a byproduct. The ASICs used in the digital power conversion process may be air-cooled. Since digital power transmission uses the existing fiber optic, wireless, and satellite internet infrastructure, no additional environmental impact is incurred. Additional carbon dioxide produced by the digital power conversion process should be offset via reforestation, using native hardwoods in cooperation with local large-scale landowners to sequester the output of carbon over long periods of time. Proper forest management will help reduce fugitive dust and coastal runoff, yield an additional valuable resource, as well as a priceless legacy for generations to come. As you can see, digital power and a digital power-based smart grid eliminate many of the problems and much of the complexity associated with today's analog grid. A digital power-based smart grid allows renewable power to be utilized when and where it is available, and economically stored and transmitted to when and where it is needed, without the need for expensive dynamic voltage regulation, expensive and dangerous chemical batteries, or hydroelectric dam-based reservoir systems designed to pump water uphill on purpose. Digital power leverages efficiency. the efficiency of using renewable power when and where it is available, and the efficiency of transmitting value by combining the existing fiber optic, wireless, and satellite broadband internet infrastructure with the high energy density of fuel and low emissions produced by a correctly tuned and operating modern internal combustion engine. The reliability of a traditional one-way analog electric utility network provides cost savings and additional income channels for the utility and third-party power providers, as well as improved reliability and rate relief to customers. And when compared to the ephemerally evolving analog smart grid and proposed billion-dollar submarine cables, digital power and a digital power-based smart grid offer significant benefits in the form of major reductions in negative impact to both the economy and the environment. Over the last 30 years, the world has watched as advances in digital computers and network technology have dragged the entrenched legacy corporations forward, kicking and screaming as they resisted the inevitable pull of digital music, digital books, digital television, digital movies, and even digital news, always to their financial detriment and often to their visibly foreseeable yet wholly unnecessary end. With digital power, the utilities can lead the way.